So conditional probability is different than the probability topics we've talked about so far because it looks at the probability of an event given that another event has already occurred. So that's the definition of conditional probability. Let's write that down. Here's the important condition. Given that another event has already occurred. Okay, so like the other parts of the probability that we've talked about, this conditional probability has its own notation. Let's become familiar with what this notation is. First of all, it starts with a P, capital P, then parentheses. Then let me just give these events labels. So event E and a vertical bar and then an event F. So this is referring to so we want to find the so the lens dropped all of a sudden. So finding the probability of event E. So this event E is the unknown one, given that event F has already occurred. Okay, so that's the definition. This is how we read it. Probability of event E given that F has already occurred. So this vertical bar is given, and this F is the known probability. Okay, so that's the notation for it. Now there's a formula with that notation, and here's that formula. We have the probability of E given F equals to probability of E intersection F divided by probability of one of these two events. Now look at this description of the notation. This is going to be one of these letters. Which one do you think it will be? Will it be E or F? Well, give it some thought. It has to be the event F, which is the known probability, right? So this has to be probability of event F. And this is the basic formula for a conditional probability. Now, the order, let me say right away that the order here matters on the left side. So probability of F given E is going to be different than probability of E given F. But this order doesn't matter. So E intersection F or F intersection E, it makes no difference. It's the same probability. So let me quickly mention that probability of F given event E would be equal to the same numerator, probability of E and F. That means the probability that these two will occur at the same time, divided by this time probability of the known event, which is E this time. So that would be E, and let me change the color for this. That would be probability of F, and this is E. In each case, the denominator is the known event, or the probability of the known event. Okay, so there is another formula, it's called the product rule, that is based on these same formulas. So I will write that here. So let me put that here, and this is called the product rule, which is equal to probability of E intersection F is equal to, just take a look at this formula. So the denominator of this is 1. If you cross multiply, you will get probability of E intersection F times 1, which is itself, equals to probability of F times that. Okay, so probability of F times probability of E given F. That is the product rule. When we get to the Bayes theorem, this will become very, very important to remember. Okay? And product rule. So let's have a look at an example just to get warmed up with working with these formulas. Remember, the formula that we've already talked about is the additive rule. Keep that formula in mind. And this is conditional probability formula, which we're just introducing. It's important to remember these formulas because these two, you can either use them by itself, each one individually, or sometimes they interact. So you find one of these terms using one formula and you plug it into the other formula. So they can interact with each other, this one and the additive rule. Okay, for this example, suppose we have two events. Let's say if E and F are events with probability of F equaling 0.38 and probability of E given F equals 0.46, if that's the case, find probability of E intersection F. Okay? So these notations speak to us in this symbolic form, right? So when you look at this description of this problem, as soon as you see this notation, that is referring you to use the conditional probability formula. So let's begin by writing the full formula for the conditional probability given this notation. So that'll be probability of E given F is equal to probability of E intersection F divided by probability F, of course, right? Using this formula. So now let's plug in with what we have and solve for the piece which we don't have. So we have plugging in for that with 0.46 equals probability of E intersection F is the unknown piece. And this is, guys, this is just one variable. So we're not multiplying P by anything. All of this represents one single variable, but it's a descriptive form of a variable. So it's telling us that this one value refers the probability of E and F occurring at the same time. This is the overlapping probability that these two events are happening at the same time. So we're looking for that, divided by probability of F, which we're given as 0.38. Okay, so we already know that the denominator here is 1. So if you cross multiply, you have probability of E intersection F times 1, which would be itself, would be equal to 0.46 times 0.38. So what is that equal to? I have 0.1748, which is the answer carried to 4 decimal places. Okay, so here's one example. Let's do another example. Suppose now we have a card that is drawn at random, right? With probability, this is always the key word, the randomness of all of this. Random from a regular deck of 52 cards. Okay, and the question is, so there are two, three questions about this. The first question is, what is the probability that the card is a red queen? Okay, so in this case, notice this is not asking for conditional probability. So we are worming our way toward calculating conditional probability. But right now there is no given. There is no what is the probability of this event given or if something else has already occurred. This is just a simple probability calculation. So in a stack of 52 cards, we know that there are 4 queens, right? So out of those 4 queens, 2 of them are red. So 4 queens, and we have out of this, so we have 4 queens among 52 cards. Right? And out of these, 2 queens are red, right? The queen of diamond is red, as you know, and also the queen of heart, which is red. The other 2 queens are queens of club. I don't know how to draw that, but this is queen of club and queen of spade, which is similar to this. So queen of spade. I forgot how to draw that, but these are the other 2 types of queens. Queens of queen of diamond, queen of heart, queen of club, and queen of spade. So 2 of them are red out of 52. So this calculation would be simply 2 divided by 52, or 1 over 26. Okay, we can convert this to a decimal value. Let me grab my calculator here. So we can do what is 1 out of 26. Let's carry this to 4 decimal places. I don't think you can see it very clearly on the screen. Maybe that's better. But I'm going to round this to 1, 2, 3, 4 decimal places. So 0.0385. So I'm rounding the 4 to 5. Okay. Part B, it's asking us to calculate the probability of picking a card that is red if we know that a queen was picked. So somebody tells us that we're blindfolded, we pick a card from this stack, and somebody tells us that it's a queen. What's the probability that it's a red one of the red queens? Okay, so this is, because of this word, it is a conditional probability. That's a clue that we have a conditional probability problem. So let's write this down. I'm going to give this label so we can better use it in a formula. R for red and Q for queen. Okay, so we're looking for probability of picking a card that is red. So that's the unknown probability if we know that a queen was picked. Queen on the other side. So this is the translation of that problem using conditional probability notation. So then by the conditional probability formula, then we should have probability of picking a red intersection queen, a card that is red and a queen card, divided by probability that we have picked a queen, right? It's all involving probability because this selection was made at random. So first we want to know what's the probability that in this deck of cards that we have a red queen card. Well, we know that there are two of those cards in the whole stack. So this would be 2 divided by 52 divided by probability of picking any of the queens. So we know we have 4 queens in the whole stack. So this would be 4 out of 52. Okay, so then this is a complex fraction, and 52s cancel out. We get 2 over 4, or 1 over 2, or also 0.5, like that. Okay, so that's an application of the conditional probability. Part C, let's ask a further question. So what is the probability that the selected card is a queen? This time let me use the other word that is a clue for conditional probability, given that a red card was selected. Okay, so we're looking for that probability. Once again, let's translate this question to conditional probability formula. So we are looking for the probability that of a queen given, or if, that translates into this vertical bar, that a red card was selected. So that's the question they're asking us to answer. Okay, let's complete the conditional probability formula for this notation, because this is our question. So probability of a queen intersection red one divided by probability that a red card was picked. So queen, a card that is a queen and red, we know there are 2 of those, right, in the whole stack. So that'll be 2 out of 52 divided by probability of selecting a red card. Because half of the stack is red and the other half is black, so we have 26 out of 52 probability of selecting any red card, right? So let's put that in the formula, 26 out of 52. Once again, the 52s cancel out. We end up with 2 over 26, or simplifying this, we get 1 over 13. So what is 1 over 13? We can quickly calculate that. So 1 divided by 13. Let me round that to 4 decimal places, so 0.0769. Okay. Okay. So let's see another type of conditional probability, or it's the same conditional probability, but it's derived from a different kind of data. It's usually, this form of conditional probability is actually most commonly used in the real world, and it's also a lot of software packages in statistics are set up to calculate conditional probability with this sort of data. So here's that example. Okay, so here we have a table that is called, it has different names. It's called frequency table. It is called contingency table. It is also called a two-way table. So my favorite name is the frequency table because the numbers in this table exactly represent that. They are frequencies, they are counts of certain random outcomes. So we want to label these columns. We have that, we have this, and we have that. Okay, so we have, in this row, we have the data for women and then men. And we have, of course, at the bottom, we have the total. Across the top, we have those who were arts and science majors, those who were education majors, those who were business majors, and of course, the final column should be the total. So sometimes you might see the table given to you without this total column and the total row. You should add those, that final row for a total and the final row for a column to the table in case it was not provided to you. Okay, so here are the frequencies. We have 342 here, 424, 682, 1,448, 324, 102, 144, 570, 666, 526, 826, 2018. Okay, so given this data, let me list the names by which, by the way, this table is known. Contingency table, two-way table, also the frequency table, which I prefer to call it. This one is better suited for this data. Okay, so given this data, we are told that a student is selected at random. So that's the key for probability calculations to be valid, right? Otherwise, if a student is selected with purpose, then that has nothing to do with probability calculation. So at random from this graduating class, and we want to find these probabilities. Find the probability that the student is male. Okay, let me just mention this. This way of organizing data is just on a piece of paper, but in real world, this whole population of the 2018 students, these are all mixed. They are not compartmentalized like you see on a piece of paper. So when we make random selection, we go to these 2018 people and just select one person at random. That's how the selections are made. Okay, so the probability that the student is male, let me scroll up so you can see the male students, the total for all graduating classes or all majors, graduating majors, is 570. So we take the ratio of 570 by 2018. So 570 divided by 2018, which is 0.282. So this is carrying our answer to 3 decimal places. So far, this was not a conditional probability, right? This is just a simple probability calculation. So part B, we want to know, find the probability of someone receiving an arts and science degree. Okay, so let me scroll back up to the data. The arts and science degrees of all both genders, women and men, the total is 666. So we divide that number by 2018. And we have 0.33. So let's ask the question to find the probability of a woman receiving a business degree. So what this is really calculating is that if any of us are blindfolded and sent among these 2018 people, and we select somebody at random, what is the probability that we select a woman who's receiving a business degree? That's what it's calculating. Okay, so going back to, so there are 2 things happening here, right? We're wondering about selecting of a woman who's also receiving a business degree. So let's go back to our data. A woman who's receiving a business degree is in that cell, right? That cell in the table is the intersection of women who are receiving a business degree. So 682 out of 2018. And we have 0.338. So far, none of these calculations have been conditional probability based. So now we're going to get to those calculations. Suppose now we want to calculate the probability of an education major sorry, no, of selecting a woman if if we know that the individual is an education major. Okay. All right. So let's translate this question to the conditional probability notation. So we're looking for probability, there it is, of selecting a woman, W, given, or if we're given, translates into this vertical bar, if we know that the individual is an education major, E. Okay, so let's complete this, the formula for this conditional probability. That is probability of selecting a woman who is also an education major divided by probability of selecting an education major. Okay, so this way of using the notation helps us set up the formula. Okay, so now selecting the probability of selecting a woman who is also an education major. We look at our data. Women who are education majors, there are 424 of those. So 424 divided by 2018 over probability of selecting someone who's an education major. When we come back here to our data, education majors are, there are 526 total of those. So 526 out of 2018. So the 2018s cancel out and we end up with, let's see, so we end up with 424 over 526, and which is 0.8806, which is the answer carried out to 3 decimal places. Okay, so that's a conditional probability calculation using this kind of frequency table data. Let's ask another question. Suppose we want to find the probability arts and science degree given that the student is a male. Okay, so once again, I hope you pause the video, write down the conditional probability formula for this, then look at what I have done. So please pause the video, answer this question, then come back to the video. Okay, so I'm assuming that you've done that. I'm going to set up the conditional formula, probability formula for this. Probability of selecting someone who is receiving an arts and science degree, so ANS, given that the student is male. So that's the question they're asking us to answer. Well, okay, let's complete the formula. Probability that somebody is getting an arts and science degree, intersection that the person is also a male, divided by probability of all those in this sample of data that who are male. Okay, so that's the full formula. So let's go to our data. We want to first locate all males who are arts and science majors. Men who are arts and science majors, there are 324 of those. So 324 divided by 2018. We divide by 2018 once again because this selection is made at random. So we are blindfolded and sent into this group of population of students, 2018 of them, and we randomly select someone. That's why it's always divided by this total in this case. In the denominator, the probability of selecting a male would be all men, which are totaling 570, and then divided by 2018. So now the 2018s cancel out. We end up with 324 divided by 570, and that gives us 0.568, which is the answer carried to 3 decimal places. Okay. So before we look at the next topic, which is the topic of tree diagrams, let me just give you one note. I mentioned this before, but I didn't write the notation down. So note that probability of E given F is not equal to probability of F given E. So these are two different probability values. Okay, I just wanted to mention that. Okay. Tree diagrams are useful in many areas of probability. So we'll do one example, and after that, I'm sure it'll be clear how they can be used. So here. Okay, so let's suppose we have 9 identical objects. And suppose that 4 of these objects are red and the rest are green. Okay. 3 of the objects. So the point of this person being blindfolded is that the person cannot cheat or rig the experiment. So the selections, these 3 selections of the objects from the container is an unbiased selection. Okay, that's the significance of it. Okay, so we have that scenario. And then part A, what we'd like to do is draw the tree diagram for this experiment. for all possible outcomes, right? Okay, so let's do that. So we'll begin with what we are given. There's a total 9 identical objects. 4 of them are red, right? So let me put a container maybe somewhere here. Somewhere here I think would be good enough, right here. So 4 red objects out of 9, and the rest are green. So 5 will have greens, right? Like that. So this blindfolded person makes 3 selections, one after one by one, and without replacing them back. So each object withdrawn is not being put back, okay? That's very important because it'll change the probability from selection to selection. So the first draw will happen right here, right? And for that, we're going to have how many outcomes? 2 outcomes, right? So one will be that, and one will be this. So we'll have a red object. Either we'll get a red object out or the person gets a green object out, right? Either one or the other. If this happens, that didn't happen. And if this happened, that didn't happen. That's why for this first draw that happens here, we have 2 possibilities for withdrawing an object. Okay, so then at this point, the second withdrawing an object happens, right? At this point. So at this point, this is the second draw. So once again, we can either draw a red object out or a green one, right? If we're here, once again, we can either pull a red one out or a green one, right? That's the second draw. So the first draw happens here, the second draw happens here. These are different scenarios. And then the third withdrawal of an object happens here, right there. Okay, at this point. So once again, if we're here, there are 2 possibilities. We can get a red or a green object out. If we're here, we can get a red or a green object out. If we're here, we can either get a red or a green one. And of course here, the same thing, either a red or a green one. Okay. So what you see on the screen now is only 5, maybe 10% of a tree diagram. Okay, maximum 10%. The rest of it, 90% of it, we haven't yet identified, which are the branch probabilities. The probabilities must be placed on each branch, and we haven't done that yet. So let's do that. So initially, to get a red object out of 9, where we have 4 red objects, so there is a 4 out of 9 probability of getting these objects out, getting a red one out, right? To get a green one out, you have 5 out of 9 probability of doing that. One thing you'll notice quickly, I'll bet, is that for each pairs of these branches, if you're doing it right, if you add these probabilities, you're always going to get 1. So 4/9 plus 5 over 9 is going to be 9 over 9, which is 1. And that's true for all these pairs, if you're doing it right. Okay? So, if we're here, then this didn't happen. The green one never came out. So we still, at this point, we still have 5 green objects
out of 8 objects, right? Because this red one is out. So we have a total of 8 objects left, out of which 5 are still green, if we're here. So to get another red one out, the probability of that, now that one red object is out, we are 3 out of 8, right? So 3 out of 8, the 5 greens are still there in the container, so 5 out of 8 possibility of getting a green object out. Okay, if we're here and we're making the third choice, that means 2 red objects are already out of 9, which means we have a total of 7 objects left, out of which there are 2 red ones, right? 2 out of 7 to get another red one out. So 2 out of 7. And none of the green ones are left if we're here. So 5 out of 7 is the probability of getting a green object out, right? So once again, add these, you get 1. 2 over 7 plus 5 over 7, 1. 3, 8 plus 5 over 8, 1. And that's true if you're doing it right, you should always get 1. In the tree diagram, this is one place, normally in mathematics, if you have, say, if you have 6 over 12, we say, don't leave it like that. Let's simplify it. Write down 1 over 2, right? If you have 3 over 9, we say, don't leave it like that. Simplify it and write it as 1 over 3. But this is one place, this tree diagram, that I recommend against that. That means if the numbers can be simplified, do not simplify them. Right? Keep them as they are, because those numbers show the counts out of the number of objects left. So this is one place you do not want to simplify these fractions, even if you can. So far, we couldn't simplify these anyway. But even if we could, I'm saying don't do that. Just keep the numbers as not simplified, because they're more descriptive. They have more information in them, these numbers, if you don't simplify them. Okay? So, if we're here, then a red and a green object are out. So we have a total of 7 left out of 9, right? Because 2 are out. Out of the 7, to get a red one out, because one of these red ones is already out, so we have 3 out of 7. So 3/7 possibility of that. To get a green one out, we have, because one green is already out, to get another green one out, we have 4 out of 7. And once again, notice that 3/7 plus 4/7 is 1, right? 7 over 7 is 1. Okay, so now to this branch, to this pair of branches. So if we're here, that means one green object is out, all the red ones are still there, because none of this happened, right? If we're here, that means none of that happened. So we're here. That means 8 objects are left, out of which 4 are still red. So 4 out of 8 probability of getting a red one out in the next try, after this try. So because one green one is out, so we are left with 4 green out of 8, so 4 out of 8 probability of getting a green object out. This is what I was saying, that when you can simplify, do not simplify. Just keep the numbers like that. Because this is just saying that, okay, at this point, you had 8 objects left and 4 were red. So if you simplify this to 1 over 2, that 1 over 2, yes, it's more simplified, but it doesn't say much about the items you have here in this container. 1 out of 2 left? No, there was, at this point, we have 8 left, 4 of which were red. So this unsimplified version, fraction, is more descriptive. It contains more information with it, which we don't want to lose. Okay, so keep it in this form. Now, if we're here, that means a green and a red object are already out of 9. So we are, at this point, we have 7 objects still left. out of the 7 objects, because 1 red is already out, we are left with 3 out of 7 red one. So 3 out of 7, and then 4 out of 7 to get a green one out. Okay, and finally, if we're here, that means 2 green objects are out of 5. So we have a total of 7 objects left, and all the red ones are still in there. So 4 out of 7, probability of getting a red object now, and the rest, 3 out of 7, is the probability of getting a green one out. Okay. Now, after placing the branch probabilities on all of these branches, our tree diagram is in fact complete. So this is a complete tree diagram. Okay, so that's that. And it says, draw the tree diagram for all possible outcomes. So let's write down the sample space anyway. Right? Let's do that anyway. So the sample space would be red, 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 right? Red, red, green. And as I'm sure you're noticing, the order matters here. Red, green, red. Red, green, green. So we're done with that. So now green, red, red. Green, red, green. Then green, green, red. And green, green, green. Like that. Okay, so how many outcomes? 1, 2, 3, 4, 5, 6, 7, 8 outcomes. That's the sample space. Okay, is the probability of all of these equal to each other? No, it shouldn't be. Some of them must maybe equal, maybe this and that equal, but they're not all equal. They have different probabilities. What we should know is that if you add the probability of for all of these 8 outcomes, you should end up with 1. Okay, they all add up to 1. Okay, so we answered part A. Part B, it says, the question asks, what is the probability of at least 2 green objects? Oops, like that. Okay, so at least 2, that's very important here. This phrase is very important. So let's identify all those possible outcomes that fall into this category. Okay, at least 2. So we're looking for probability that more than the number of greens is either 2 or more than 2. Right? At least 2 means either we're looking for 2 greens in an outcome or more. Okay? So let's see. Which one of these falls into this category? Does this one fall into this category? No. There's no green here. Does this one fall into this category? No, because there's only 1 green. How about this? No, 1 green. How about this? Yes. We have 2 greens in that outcome. So probability of anything equal to 2 greens or more includes that. So let's write it down. Probability of red, green, green is included here. What about here? No. There's just 1 green here. How about here? Yes. Once again, we can include that. So plus probability of green, red, green, plus how about this? Yes. Once again, we have 2 greens there, which is the minimum we're looking. How about this? Absolutely. That has more than what the least at least is, so that is for sure included part of this. So probability of green, green, green. Okay? So these 4 events are part of what we're looking for, part of this probability. Okay, that's the probability of at least 2 green objects. Okay, so now how do we calculate the probabilities? Well, for each of these, simply multiply the branch probabilities for it. So red, green, green, red, let's see, red, green, green. So for the probability of red, green, green, multiply 4/9 by 5/8 by 4/7. That's the probability of red, green, green. Okay, so let's do that. I don't think I can keep everything on the screen, but let me try. Okay, that's as far as I can get it. So, for red, green, green, you can see it on the screen, 4/9 times 5/8 times 4/7. Okay, plus green, red, green. That will do green, red, green. So 5/9 times 4/8 times 4/7. Like that. Green, green, red, that would be green, green, red. So 5/9 times 4/8 times 4/7. Okay, plus green, green, green. So that's 5/9 times 4/8 times 3/7. Like that. So we need to add, we need to do the arithmetic basically on this. So this 4 times 5 times 4, that's 80. 9 times 8 times 7, that's 504. Plus, once again, multiply those, you get 80 over 504 plus, once again, 80 over 504. So far they're equal, but the last one is not. So we have 60, right? 5 times 4 times 3 is 60 divided by 504. So we'll get 300 divided by, add all of those, you get 300 divided by 504, and that is equal to 0.595. Okay, rounding the answer to 3 decimal places. Okay, I hope this is making sense. Once you have the tree diagram, the rest is easy. Okay. So part B, or C, they want us to find the probability that no red object was selected. Okay, no red object was selected. So we're looking for probability of no red object, right? That's the question mark. So let's bring this back. Here's the tree diagram with the sample space, right? No red object, that means this one has red, this one has red, 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 and the only outcome that has no red in it is this last one, which is, I mean the last one in the sample space, but it's that branch, green, 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 right? So what we're really looking for here is probability of having a green, green, green outcome. That's what we're looking for. And what is the probability of that? 5 nines times 4 eighths times 3 over 7. So let's write that down. And this will be 0.119, like that. Okay? Again, rounded to 3 decimal places. Part D, we want to find the probability of a green object were selected. Okay, the probability of a green object given. Do you remember this? This is a, what is this? Do you remember it? It's conditional probability. That's the clue, that you're looking for a conditional probability there. Probability of a green object given that 2 red objects were selected. So let's bring this, so basically, let's translate this before we look at the tree diagram. Let's translate this into proper conditional probability notation. Probability of a green object given, right, that 2 red objects were selected. Okay, that's what we're looking for. So let's bring this back, our tree diagram. Probability that a green after 2 red objects were selected, right? Here's a green object after 2 red ones were selected. So what's the probability of that? 5 over 7, very easy. So the probability of selecting a green object after selecting 2 red ones is simply that branch probability. We don't need to do any more multiplying or adding. It's just that, 5 over 7. Like that. Okay. So let's do another tree diagram problem or example. So suppose we have this following tree diagram. This time the tree diagram is given to us. Okay, suppose we have, let me see how I can fit this. I guess if I put it here, it'll fit nicely. 3A, 5B, and 6C, like that. Then we have that. So we have A, B, and C. So we have the three letters A, 5 letters B, 6 letters C in this container, right? And we make two draws. But that's not important because the tree diagram is being given to us. So I'm just going to draw it. C, and the probabilities are as follows. So we have 3 over 14 5 over 14, 6 over 14. Here we have 2 over 13, 5 over 13, and 6 over 13. Then we have 3 over 13, 4 over 13, and 6 over 13. And we have here 3 out of 13, 5 out of 13, and again 5 out of 13. Okay, so we have that. And the question we're being asked are as follows. Part A, we want to know what is the probability of A given B, right? Here's the conditional probability clue again, right? What's the probability of getting an A if we know a B has already been selected, right? That's not it, because here we have an A selected, then an A. We're looking for an A where B given B, so it's that one. So probability of A given B, that is that one, 3 out of 13. Okay. Part B, we want to know, let me move this up. So like that. So we want to know the probability of C given A, right? So we're looking for probability of C given A. That's what we're looking for. And again, this is conditional probability. Right, like that. Okay. So what's the probability of getting a C if A has already occurred? Is that the one? No, that's B occurred, then C. We're looking for C if A has a given A, so it's that one. Right? Probability of C given that A has already occurred. So it's 6 over 13. That one. Okay, 6 over 13. That. Okay, one more part, part C. We want to know the probability of B given C. Okay, once again that conditional probability clue. All right? Okay, so we're looking for probability of B given that C has already occurred. Right? Probability of getting it B if we know C has already been picked. So C has already been picked, that's that, and probability of B, that's 5 over 13, right? Probability of B given that C has already been picked. This is C. Okay, so that's 5 over 13. That. Okay, so let's look back at some example of using conditional probability with Venn diagrams, right? So this was an example of using conditional probability with tree diagrams. So next, let's look at conditional probability and Venn diagrams, among other things, right? So we'll just review Venn diagrams again. So given Austin, Boston, and Chicago, you remember this example, right? But this is I'd say 90% like that, but I've modified it to fit this context in this section. So it's a little bit, the data is the same, but the way we're going to use it, some of the data is being changed to make it suitable for this example. Just be aware of it. But we've seen this example or very similar to it before. So we have this group as this circle representing Austin, those who visited Austin, those who visited Boston, and then those who visited Chicago, right? So we have 8 people here who visited all 3 cities, 7 who visited Austin and Boston, and then 13 just Boston, 10 just Austin, 23 Austin and Chicago, 20 Boston and Chicago, but not Austin, and then 14 just Chicago. So let me, well, by the way, so I should actually draw a box around this. Five. Okay, so let's make sure that we understand these numbers. These 5 are 5 who didn't visit any of these 3 cities, right? Not Austin, not Boston, not Chicago. That's these 5. By contrast, these 8 visited all 3 cities, Austin, Boston, Chicago. And remember what we said, that whenever you draw a Venn diagram, you always want to start from the innermost overlapping section and work your way out. So then you would go filling in these spots, the 20, 23, and 7, and then the 10, 13, and the 14. Okay, so what does the number 7 represent? The 7 represents those who visited Austin and Boston, but not Chicago. Okay, not Chicago, just Austin and Boston. If I say, what's the, how many people visited Austin and Boston, and I leave the word not Chicago out, then you can include 7 and 8 together. You can say 15, because I didn't say how many visited Austin and Boston but not Chicago. I didn't say but not Chicago. So you can say 7 and 8, 15 total. Okay? If I say how many people visited Austin and Chicago, right? What would you say? You would say, well, Austin and Chicago, 23 plus 8, 31. But if I said how many visited Austin and Chicago, but not Boston, then you would say 23. Okay? So language is very, very important in probability. If I say, I'm going to repeat this again because it's so important. If I ask you, or if a question asks, how many visited Austin and Chicago? Right? You would say 23 plus 8, 31. But if I revise my question and say, how many visited Austin and Chicago, but not Boston? Then you would need to exclude that. You would only end up with 23. Austin and Chicago, but not Boston, that leaves the 8 out. Because these 8 not only visited Austin and Chicago, but also visited Boston. So if you say how many visited Austin and Chicago, not Boston, you want to exclude those and you just say 23. Because these 23 visited Austin and Chicago and not Boston. Okay? By the same token, if I say how many visited Boston and Chicago? If I ask you that question, what would you say? How many visited Boston and Chicago? You would say 28. Boston and Chicago, that's that whole region, that's 28. But if I say how many visited Boston and Chicago, but not Austin, how many? You should say 20. Because these 20 are the ones who visited just Boston and Chicago, not Austin. Okay, Austin is left out. Because these 8 visited Boston, Chicago, and Austin, all 3 cities. Okay? I hope this is making sense. Okay, so given that Venn diagram, here are the questions they're asking us. Okay, so what's the probability that someone did not visit any of the cities? None of the cities, right? We have 5 of them, and they're asking for the probability. Not count, but the probability. So 5 out of a total, right? So this probability is 5 out of 100, or 0.05, right? Now let me ask you this. This problem is saying, given the Venn diagram below for 100 college students, so they're telling us how many college students were surveyed. But do we need for us to be told that information? Do we? No. We don't need them to tell us 100 college students were surveyed. Well, if they don't tell us, how can we calculate this? Well, just add these numbers. These numbers should add up to 100. So if this information was not provided and we still had to calculate this probability, we know that we would need this 100. How could we get it if it's not been provided? Simply add all of these numbers. So 5 plus 14 is 19, plus 20, that's 39, plus 13, that's 52, 52 plus 8 is 60. 60 plus 23 is 83. 83 plus 7 is 90. 90 plus 10 is 100. So you don't really need this information, but it's been provided. So you don't have to add these numbers. But if this number wasn't there, you could easily get that by adding these numbers and dividing this number, which is the number of people who did not visit any of the cities, by the total, which is 100. Okay? All right. So part B. What is the probability that someone visited all 3 cities? Okay, so that's 8 people visited all 3 cities, but they're asking not for the count, they're asking for the probability. So that count divided by the total. 8 over 100 or 0.08. Okay. Part C. We want to know the probability that someone visited Boston but not Chicago. Okay, Boston but not Chicago. So these, notice that, let's see. So these, someone visited Boston but not Chicago. So we have, how many we have? We have 13 visited Boston and nowhere else. So that's part of it. Boston but not Chicago. We have those who visited Boston and Austin but not Chicago. So 13 plus 7, that's 20. So these 20 visited Boston but not Chicago. So they're still part of this probability. Then we have these 8 who visited Austin, Boston, Chicago. We don't want that because we don't want anybody who visited Boston to have visited Chicago. Not that, not them. And these 20 visited Boston and Chicago only. So we still don't want that. Okay, we don't want any of these, but we want these 2. So 13 plus 7 over 100. So we have 0.20. Oops, sorry. I was off the screen. Okay. So 13 plus 7, that's those who visited just Boston. 7 is those who visited Boston and Austin, but not Chicago. We have to exclude these 28 because in one form or the other, they visited Chicago. So we don't want these people, but we want these people. 7 plus 13 is 20, divided by 100 is 0.2. Okay. So D, we want to know the probability that someone visited Chicago but not Boston. Yeah, so this is the opposite of C. Someone visited Chicago but not Boston. So in other words, We don't care if somebody visited Chicago. I mean, we do care that somebody visited Chicago and Austin. That's okay, but not Boston. We don't want somebody who visited Chicago and visited Boston. Okay? So, someone visited Chicago, but not Boston. So that would be 14, right? Plus, we want these people, because these 14 people visited just Chicago, nowhere else. So we do want that. Do we want these 20? No. Because these 20 visited Chicago and Boston, so we don't want that. Do we want the 8? No, because these 8 visited Chicago, Austin, and Boston, which we don't want, so we don't want that. Do we want the 23? Yes, because these people visited Chicago and Austin only, but didn't go and visit Boston. So we want the 23 and 14. So 23 plus 14 over 100, and that'll be 37 over 100, or 0.37. Okay, part E. So far, none of these were conditional probability, right? But now, let's do a couple of examples on the conditional probability. So what is the probability somebody visited Austin given, right, that's an important phrase, right, or word right there, given that the person had visited Boston. Okay, all right, so let's translate this into symbolic form before we look up the probability values, right? What's the probability that somebody visited Austin? So that's that, given that the person visited Boston, like that, okay? So from the conditional probability formula, we can write probability of A intersection B divided by probability of B, right? Okay, A intersection B. So let's see, that's Austin and Boston, those who visited Austin and Boston. Austin and Boston, that's that region. These people visited Austin and Boston. It's okay, this 8 also visited Chicago, that's fine. That sentence, that problem or question doesn't say not Chicago, so 8 is also included as part of those who visited Austin and Boston. Okay, so 7 plus 8, that's 15 divided by 100 divided by, because that's a probability, right? So 15 out of 100, or 7 plus 8 out of 100. Now this is probability of those who visited Boston, all of those who visited Boston, right? So that would be all of these people who visited Boston in any category. 13 plus 7, 20, plus 8, 28, plus 20, 48. So we have 48 divided by 100. So the 100s cancel out. We end up with 15 divided by 48, which is equal to 0.3125 carried out to 4 decimal places. Okay. All right, so let's do another one with conditional probability. So we want to know the probability that somebody visited Chicago given, right, very important word, indicates conditional probability, given that the person had visited Austin. Okay, so before we go to the Venn diagram, before we go to all that number, let's translate this sentence, this question, into symbolic form. So we want to know probability that someone visited Chicago given that the person had visited Austin. So that is what they're asking. So let's complete the conditional probability formula for this. We have probability of C intersection A, that is those who visited Chicago and Austin, divided by probability of the given, probability of those who visited Austin. Okay, so those probability of those who visited Chicago and Austin. Let's go back to the Venn diagram. Chicago and Austin, right? That would be that. That's all these people in this region, including that, because that question doesn't say probability of those who visited Chicago and Austin but not Boston. It says Chicago, so it doesn't say not those people. So we include them. So Chicago and Austin, that would be all of that. Because 8 are people who visited all 3 cities. 23 are people who visited just 2 cities of Austin and Chicago. And together it will be 31. All right? So 31 divided by 100, because they're asking for probability of that, divided by probability of all those who visited Austin. Well, all those who visited Austin are all these people in every category, right? So 17, 10 plus 7, 17, plus 8 is 25, plus 23 is 48. So 48 divided by 100, because it's probability. All right, so the hundreds cancel each other out. We end up with 31 divided by 48, and that is equal to 0.6458, which is the probability answer calculated up to 4 decimal places. Okay, so we have come to the conclusion of another section for 8.1 this time. I hope things are making sense, and so for now, have a nice day, and I'll see you again next time.